EDX Mechanics 1, Work, Energy and Power 1, Work and Energy, Potential Energy. Mechanical energy due to an object's position is known as potential energy. You can think of potential energy as the energy stored in an object which gives it the potential to move when released. The two main examples are gravitational potential energy, or GPE, and elastic potential energy, EPE. Here we will be considering gravitational potential energy, and will only deal with the energy stored in elastic springs and strings at a later stage. So, work done by and against gravity. All bodies with mass experience a gravitational pull from the Earth. The force that acts upon them is their weight, which is proportional to their mass. So the weight equals mg, where m is the mass in kilograms and g is the acceleration due to gravity, 9.8 meters per second squared. So if an object moves in a vertical direction, then it is moving either under the action of or against the action of its own weight, depending on whether it is going upwards or downwards. Hence, work is done by or against the weight, and by the work energy principle, the object either gains or loses energy. This change in energy is called its potential energy and is W times the height, which is mgh, where h is the change in the height of the object. If an object is moved from the surface of the Earth to a height h, then the work done against gravity will be mgh, and this is what is known as its gravitational potential energy. This stored energy has the potential to become kinetic energy when we let the object go. So an example of this is the hydroelectric scheme. When the sluice gate is closed, there is no movement of water. However, the height or head of the water gives the water its gravitational potential energy. When the sluice gate is opened, the water rushes down the pipes to drive a turbine. i.e., the water now has motion and hence it has kinetic energy. So its initial potential energy due to its height has been turned into kinetic energy due to the drop in the height and the gain in the speed. So for example, if a particle of mass 30 grams is pushed 2 meters up a plane inclined at 60 degrees, find its gain in potential energy. So it's important we define where zero potential energy is. So I'm going to define zero potential energy at the bottom of my diagram B. So I'm going to say that that is my zero level of potential energy. So at A, my final potential energy will be mgh. So my mass is 0.03 kilograms. Gravity is 9.8, and we need to know the height of the object, the height that it has travelled through. So although it's travelled 2 meters of distance, its height gained is h, and we can get h from the diagram by doing some trigonometry as 2 sine 60 degrees. So the final potential energy is 0.509 joules, and therefore the gain, it started with 0 and it's ended up with 0.509, so the gain in potential energy is 0.509 joules of potential energy gained. So here we have an object of mass 5 kilograms. It's initially held stationary 10 meters above the ground. It's then released and allowed to hit the ground. We want to find the initial gravitational potential energy, the kinetic energy at the instant it hit the ground, and the work done by gravity. So the first thing we need is our initial potential energy. So I'm going to define zero potential energy as the level of the ground. So my initial potential energy is going to be mgh, so that's 5 kilograms, gravity 9.8, and the height above my zero level is 10 meters, so that gives me 490 joules of potential energy initially. We want to find the kinetic energy just at the moment it hits the ground, so I need to know how fast it's going. I can work out how fast it was going just as before it hit the ground by doing v squared is u squared plus 2as from the top to the bottom, and I'm going to take downwards as positive. So the speed v just before it hit the ground is what I'm looking for, so that's v squared. The initial speed as it was released would be 0. The downward acceleration is gravity, so that's 9.8. And the downward displacement is 10 meters covered. So we get v squared is 196. But we want the final kinetic energy. So the final kinetic energy using a half mv squared is a half times the mass, which was 5, times v squared, which we've just found is 196, and the final kinetic energy is also 490 joules. So this simplistic question gives me two interesting results. Because there was no air resistance involved, we've just shown that the potential energy lost as it dropped and lost height is exactly the same as the kinetic energy gained due to conservation of energy. And the other thing we've discovered is that the work done by gravity, which is what we've been asked to find, we know the work done by gravity will be the potential energy lost in this case. So the work done by gravity is also 490 joules of work done by the gravity, as we can see there. So in the next session we're going to be looking at conservation of energy.